Welcome everyone to another instance of the Northwest Database Society Symposium, and this is part of the Microsoft Talk series, so thank you Microsoft for sponsoring. Today we're very happy to have with us Professor Azza Abouzied from New York University, Abu Dhabi. Azza has a PhD from Yale University. Her research is in a very cool area at the intersection of databases and human-computer interaction. What I think is really cool is Azza has actually best paper awards from both communities. So it's great to have some from one, but have some recognitions from two communities. It's really exceptional, and we're super happy to have her today talking about how to query time series data with sketching. So thank you for being here.
Thank you, Magda. Thank you for hosting me and for that great introduction. I wanted to go a little bit about myself because I'm traveling to all these different places, and I don't think people are familiar with what I've been doing. So I graduated at around 2013. In my PhD, I started out doing pretty much back-end systems database research, and then I switched to a more HCI flair, but also still sort of helping people with data analysis tasks and with database queries. I joined NYU, and I'm actually on a campus across the ocean, across the Atlantic, in Abu Dhabi in the UAE, and we're at a place called Happy Island. So you could tell we're very happy over there, and we're doing great research. A lot of my work, or most of my projects, are at this intersection between HCI and databases. SEER is around data extraction. Catch, which is what I'm going to be talking about today, is around time series querying. YFlow is about debugging, and Sinner is about generating data. And all of these projects really have the end user in mind. So we built these systems thinking specifically about how people, for example, want to generate data or how they want to give examples of what it is that they want to generate. I do also have some very much database-y problems or systems database problems. And there's a package builder, stochastic package builder, this new project around Markov decision processes in databases. They're all around adding a new interesting feature to a database, and how do you build your query optimizer, how do you build your query planner, how do you execute these queries within a database. So all of these are projects that you could ask about me later, but today I'll be talking about Catch. In addition to all of this, I have a recent baby, a new addition to the family, and he's been proving well, he runs the show, but he's also the biggest challenge I have met so far. So this is Musa. He's with me on this trip. All right. Okay. So this paper was published in CHI 2018. Miro Menino is my research assistant, and it has received a best paper award. And the question that we're really answering or what set this project out is we wanted to sort of figure out how do people sketch time series queries when given a scale-free canvas. So if you have time series data and you want to look for a pattern in it, how do you search that pattern if you're only afforded a canvas that has no scale to it? Right? And the idea is that our users are going to sketch freely the pattern that they're looking for. Well, what does that mean? What do these sketches look like? And so we set about doing this intensive crowd study to figure out what do the sketches look like. And the way the study worked was we showed the users, or the crowd workers, different time series data. For example, these are Amazon stock prices. And then we showed them a region of that time series, and we asked them to sketch it. Right. And these are all examples of sketches that we got. So we sampled around 150 workers. We gave each one of them about 8 patterns. And then we verified these sketches, also using the crowd to sort of ask the crowd, does this sketch really match this region? And we collected a total of roughly 1,000 sketches, and this data set is available for you to download and use for your own research if you want to. All right, so what is it that we found when we looked at this sample of sketches? Well, we found a number of things. Well, the first one is that they preserve these visually salient features. right? So the main features that you look at this region is that there are 3 humps, and all the sketches have more or less 3 humps in them, right? These are the visually salient features. But what the people didn't do is go and do all these micro fluctuations in the pattern, right? They really picked at what was important. The other thing that we noticed, remember it's just an empty canvas, was that there was no respect to the aspect ratio, right? They didn't try to match exactly the sketch. In fact, if you look at what this sketch is, it's much bigger in terms of it's much bigger than what they saw visually on the screen, right? And it's the aspect ratio was off. This is flattened out a bit more, right? So there's no respect for the aspect ratio. And what we call that is non-uniform global scaling. So if you overlaid the sketch over what the time series was, they wouldn't match directly. And then if you try to sort of scale it so that it matches, we noticed that there were lots of local distortions, right? So we take this sketch, we overlay it so that the height and width are the same. We scale it that way. And then we look at, the thing itself, and there are local distortions. So this hump is much wider than what it's supposed to fit, right? So there are always these small local distortions. Now, none of these are surprising, right? And there's actually a beautiful paper about how humans sketch. This is what my 5-year-old nephew drew when I asked him to sketch President Trump, right? So you notice there are some visually salient features, the red tie, the beautiful hair. Local distortions, the hands are very big. We know that to be a problem. And there's global non-uniform scaling, right? This is not the scale of President Trump, right? This is a tiny sketch, and it's a bit, it might be a bit narrower. Like if you stretch it out proportionally, it won't be President Trump in terms of size, right? That's what we mean by non-uniform rescaling. Okay, so this is how people sketch time series. Now we want to use their sketches to sort of search for patterns in time series data sets. Now you might be thinking, hey Azza, there are tools that do this, right? Why can't we just use these tools? Now the trouble with existing tools is actually the algorithms that they use to do the matching, right? And the 2 most common ones are what we call dynamic time warping or Euclidean distance. And fundamentally, these tools are very good at matching one time series to another, but they're not good at matching a sketch to a time series, right? And the reason is they do require query length. Now, if you read the literature on dynamic time warping, it would say, no, you don't need that. You are allowed to warp, right? And what a warp basically is a stretch that you can afford at the time scale. But you have to specify that warp size, right? So even though they can support to a certain degree some distortions at the time scale or even the amplitude scale, you need a lot of fine-tuning of the parameters that these algorithms have. To get DTW to work correctly, you need to provide not only the query length, but also things like the warp size, the step size. You might need to normalize your query and normalize your data set. Or you might need to do some sort of shifting and mean offsetting to sort of get it to work. And the problem is that the tools that we have are built on top of these algorithms, right? So we have a bottom-up UI design rather than a top-down. We did not think about how users sketch queries and then design the query matching algorithms. We designed the query matching algorithms, and now we design their interfaces to work with them, right? So this idea of using sketches exists in the literature. The earliest one is this work by Martin Wattenberg, where basically you have to sketch to the same scale. So they show you the time series data, and you sketch to the same scale. And that immediately gives you the query length, right? And if you're not doing that, there are some other work. This is most recent work by Holz and Feiner, and it's a great paper, where you sketch over the pattern that you want, but then you allow yourself to vary a few things. So, like this is the underlying data set, and then you sketch over it. This basically tells the system that you want to tolerate this much distortion in terms of amplitude at the top of the hump and at the bottom of the hump, right? And the sideways variations tell you how much you want to relax your temporal scale. But again, you're sort of dealing with algorithms that exist at the bottom, and these algorithms require a query length or require a warp size or a step size. We don't have these problems. We fundamentally said, we're going to give you a canvas, you draw it at whatever you want, and then we're going to match these patterns. And this is kind of important because how you visualize a time series can greatly change what the pattern is. If you just think about a straight line at a 45-degree angle, now if I stretch my visualization, that line can become almost flat, and if I compress it, that line becomes almost vertical, right? But in all cases, I could visualize my time series so that it exactly matches the 45-degree angle. Right, so scale-free, drawing a sketch on a scale-free canvas sort of opens up what you can match to that sketch. Right? So if they're not doing overlays, if they're not sort of annotating an existing time series to look for queries, other kinds of tools sort of did sketchless querying. So they kind of dropped this whole idea of sketch to find a similar pattern. Time boxes by Ben Schneiderman, and I can't pronounce this guy's last name, sort of do that, right? You specify ranges that you want your time series to go through. This is interesting work by Keogh and Smith, where they basically let you sort of, there's no more sketches. You can either draw straight lines, so you can't go all curvy and stuff, but so they've restricted how you can draw your sketch, but then they sort of allow you to match these restricted shapes to sort of linear segments within the time series. So again, they've changed completely how people would naturally specify what they want the time series to look like so that it works with their algorithms, right? With Catch, we said, no, forget about this. Let's do top-down design. People are comfortable with sketching. How can we support sketching as a way to do querying over time series? And that led to the catch matching algorithm. So it's a very simple algorithm. The first step in it is a bit of pre-processing, right? We basically take our data set and we generate multiple iterations of it at different smoothing levels. And the way our smoothing algorithm works is, as long as we're changing the number of segments that we could extract, we continue smoothing until you cannot create any more segments. And what segments are is basically anything where the gradient doesn't switch from positive to negative is a segment. Right?
I just want to understand, the problem here is that you're giving a sketch and you want to find matching time series.
Right.
Yeah. Okay. So for each smooth iteration, I get different segmentations of it. And basically, segmenting is basically, this all has a positive gradient, this all has a negative gradient. The gradient value can change, but the signal is the same. And then I take my query and I segment it, and I have my candidate regions that are also segmented. And now I'm doing segment by segment matching. No query length. I don't care how big or how small the segments are. Right? So now if my query has 4 segments, I'm looking for a match that's 4 segments long at different smoothed iterations of the data. Right? So that allows me to operate at multiple timescales. Okay. And then what I do is I rescale this query to fit the candidate region. Right, so remember that users are not good with aspect ratio, so I don't really care for that. I take whatever they've drawn and I stretch it out so that it fits the height and the width of the candidate segments that I'm matching. Okay. And then after I do that rescaling, I look at what I have. And basically, I notice that there are some distortions when I try to match this query to this blue data region, right? And that gives me a distortion error, a local distortion error. Okay? And that local distortion error is basically, what do I need to do to just rescale this segment so that it fits the data? Okay? And then after I do that, after I stretch this part so that it fits, I get shape errors, right? Sure, they fit in terms of height and width, but there's actually differences in what the user sketched and what the data is. And so I use distance measures, and I could use any distance measure. We've used Euclidean distance. You could use Manhattan distance. Any LP norm distance would work. And that gives me a shape error. And because I have the distortion error computed separately from the shape error, I could control how much weight I give to each of them. And that allows me to say, you know, well, people are more prone to distortion errors, or distortion errors shouldn't weigh as much as they would when doing pure Euclidean distance, right? One of the problems with pure Euclidean distance, or even DTW, is if there's a distortion, it weighs a lot. And if you think about it, when people want to say, I want you know, a head and shoulders pattern, it could be that the humps are made much smaller than what they're supposed to be because they want to emphasize that they're smaller than the middle hump. Right? So the users have a tendency of overemphasizing what they intend. And this is what the local distortion tends to grasp, right? Or if they want to point out that something is narrow, they'll make it overly narrow. Okay? So then I rank all my results, all my candidates, by the distance, right? Or by the error. The bigger the error, the further away it is from being the result. So what does the catch matching algorithm achieve? Well, it supports sort of scale-free sketches, and it preserves visually salient features because it does this segmentation and segment-by-segment matching. And also because it does smoothing and it operates at different smooth operations, we could match to any time scale, right? And this pre-processing isn't bad. Like a lot of people say, oh, you're doing all these smoothing iterations. Well, it's not really that bad. It's on the order of, for every time series, we have log number of data points in that time series, smoothed representations of it. So it's not that bad. We're not creating that. We're not really exploding the data set in any way. Okay. We support this global non-uniform scaling because we don't have a cost for basically stretching the query segments to fit the data segments, right? And we support this idea of local distortions by basically controlling the weight of the local distortion, right? And it's not given as much weight as it would have been given if we're doing Euclidean distance, right? I mean, the one way to think about it, okay, there's no board here, but that's all right. If this is done with Euclidean distance, then basically the difference between this and this is computed as a point-by-point difference, right? So that local distortion is blown out of proportion in terms of the error that it gives or the distance that it gives, right? But to us, it's just the rescaling factors that I apply, right? And I weigh that in a more reasonable fashion. Yes.
So when you showed us at the beginning the different ways people were sketching, some people just kind of draw the main, right, kind of frequency if you want. And other people would actually go through the trouble of showing that there's also some little things.
Right.
But it seems like with this strategy, it doesn't matter if I show the small wiggles, because it's really the big wiggles that are going to be the most of the matching.
Yes.
Kind of account for most of it. But maybe I really care about there being little wiggles.
So the thing is, we've seen this sort of adding the noise in about 9% of our sketches. So it wasn't that big a thing. But even then, we would still do better. And the reason we would do better is if the user adds those wiggles, then to us, we emphasize that that's an important part of the sketch, right? So those are given considerable weight. Each of those becomes a segment in a way, right? And we would still match with the time series data set, maybe not as well as if they had went liberally, but we're still better than the other algorithms, even with that 9%. But the thing is that most people didn't do that. Like, most people didn't add noise. Okay. The other thing, like, we've also experimented with smoothing the query segment. And we didn't realize that we needed more than just removing hand jitter. All right. So I'll show you a quick video demo of what Catch looks like. Is there no play button here? Okay, it's working. So you notice here the user is freely sketching what they want. There's no scale specified. Across different smooth iterations, we've computed different matches. Now we rank them by the most likely match. So you could go through the different smoothing iterations if you want to control the time scale that you're interested in. Or you could just go here and pick the thing that with the highest rating, or the highest, the lowest distance, or the lowest error. And so we've ranked them so that it will pick out this as the best match. And actually, the second best match is the head and shoulders hump right next to it. Okay. Now, there are other features that allowing the user to draw on a canvas gives us, right? And so once you've framed the world and, okay, the user is going to sketch on a canvas, there's so much power that you get from that, right? Part of the power that we get is this idea, okay, well, what if I allow the user to annotate a sketch? Not just ridiculous simple annotations like query length or amplitude. I mean, we could allow them. Those basically are filters. But what if we allow the user to basically add regex annotations? And that's basically what we do here. So in this query, they drew this hump, and then they said, well, I want this big hump to repeat. And so now it's just an annotation over the sketch. And they've annotated the sketch with a repeat operator, and now it's looking in the data set for patterns where there are two big humps followed by a small hump, or multiple humps and a small hump.
About the technical detail here. So you said that you're sketching the annotation to remove this difference between small humps and big humps. Mm-hmm. But here apparently that the distinction is important.
No, so we're not removing that. There is an error that's added, right?
Much smaller than.
Yeah. So just by being smaller than this, there is a distortion error that we add to the overall cost. But that error does not overwhelm the cost like it would when we're doing the Euclidean distance, right? And so it would prefer a big hump and a small hump, right? And of course, we don't want to eliminate these differences. In fact, we want to emphasize them in a way. Okay. So we could do regular expressions over sketching. Now we take this idea a bit further. If I'm having them draw in a sketch, what if they could draw things that are spatially apart, right? So what we try to do is, can I let them sketch things depending on where they drew them, sort of use that to order which pattern should arrive before the other. So in this case, I'm looking for a depression pattern, sort of an increase in unemployment and a drop in equity, and I want them to overlap. So this is me querying two different time series data sets, but because I've put one above the other, or sort of in the same position on the X scale, it looks for them in the overlap. And I could do the other thing, sort of this demo went a bit faster than I anticipated. So here the order of them, sort of on the X scale is that they're in the same place, so I'm looking for patterns that overlap. But I could also say, well, I want this pattern to occur before the other, right? And that would look for some patterns where they're not overlapping, but one precedes the other. Right? So we're stretching this idea. If I have a free canvas and I'm sketching patterns on it, can I use the order or the relative positioning of where the sketches are to control the order of where these time series appear? And I don't have to do this on different time series. I could do it on the same time series itself. And so I could look for patterns that are a gap apart, for example. Okay. So this is the gist of Catch. It's a very simple idea, right? We had a very clear purpose at the beginning. We wanted users to sketch freely what they want, then we extended this idea to support time series query. Well, how did we perform? Was it good or bad? So we did two kinds of tasks. One is targeted search. There's a specific pattern that you're looking for, and we want to see how well we did. Now, the great thing is we have that data set of 12,000 sketches that we have. So we could look at them and see, well, how well did they help us sort of extract the reference region they were based on. Right? So remember at the beginning we did a crowd study. We had 8 reference regions. We asked Mechanical Turk workers to sketch based on these regions. Now we're sort of doing the reverse, right? We have the sketches that they drew. What is the result of that reference region when we use DTW versus Euclidean distance versus us? Right? For most of the queries, we do better. So right here at the one line, that's DTW. If we do better, then we're above. Right? And we're basically computing the precision at 5. So the first 5 results, did we return the reference region or not? And so here, for example, for the head and shoulders pattern, we have above a factor of 2 improvement over DTW. Euclidean distance is in fact better than DTW, but we're better than Euclidean distance. Okay? And the thing that you should consider is that both DTW and Euclidean distance have query length. Right? And so these are not huge data sets. So if I have the query length and I have the shape of my query, then I could do quite well with these algorithms. Right? So the fact that we're beating them is quite telling.
So you're saying that they have actually the fragment of the time series, I mean, the query event means the actual time series you're looking for?
Yes. So remember, we have a specific reference region,
Right.
a specific area in the time series that we want, and we ask them to sketch that.
Right.
So now we use the sketch to query, and then we see what rank does that reference region appear in. If it's in the top 5 results, then we know we did well, right? So now we're just looking at DTW versus Euclidean distance versus us, and saying which one of those put that reference region in its top 5 results.
But if you give them the exact time series that is a reference region, then the Euclidean distance should find it because
Well, we're still doing
0.
sketching, right? We're matching the sketch to that area.
Okay.
Yeah?
The Euclidean distance between the sketch and the...
Right. We do expand the sketch, though, so that it's exactly the same query length and height as each region as we're stepping through. So my point is that we're giving DTW and Euclidean distance their best operating circumstances.
By scaling appropriately.
Exactly. Exactly. And so we're still doing better than them. And DTW is the state of the art, right? Almost any time series paper has DTW at its heart, with some variation sometimes. Now, we're not always good. For example, here at this rounded bottom pattern, we're much worse than DTW and Euclidean distance, but that's because it's a very simple pattern, right? And they have query length. We don't have query length. So basically, any downward segment like that, we match to it. Right? Okay. Yeah, so I think it turns out that 5 out of the 8 queries, we beat DTW, and 6 out of the 8 queries, we beat Euclidean distance. And most of them have to do with things like, how simple the pattern is and what the influence of query length is. Right? Okay. And actually, for this specific one, there was one big trough that was of a certain length that we were looking for. Right? So the entire data set was just different noise and then one big trough. So if you had query length, you had the results pretty much. Okay, well, targeted search is kind of like a Troy experiment, you could say, and it is fair to say that we are sort of studying how we perform based on a data set that we've generated, and so we've perhaps engineered for that data set, right? So then we say, well, how did we perform in exploratory search tasks, right? So basically here, it's free querying. We ask the users to sketch whatever they want, and then look at the results and rank how relevant they are. Right? And we ask them to do this for DTW and catch. And then we computed what we called the normalized discounted cumulative gain. And basically, the closer you are to 1 in this metric, the closer your ranking is to what the user's ranking is. right? So NDCG basically compares rankings. And you can see that for most of the queries, each of these lines represents the NDCG graph for a specific user. Catch sort of outperforms DTW. So again, even in exploratory search tasks, where we ask the users to freeform, draw any query they want, we perform better than DTW. So actually, that's it for Sketch. There are lots of other projects, as I said, that I'm working on that have that similar flavor, where we study how the user actually wants to do a specific data task naturally. And then we see, well, what does that mean in terms of how we've designed our actual systems or our actual databases or our actual platforms? And one idea that I've been sort of playing around with is that users are very comfortable at specifying their tasks through examples. Right, so my first work was sort of data querying by examples, where the user sort of gave us examples of things they want in their result set or things that they don't want. And from that, we sort of reverse engineered the query. So that's data play. These are other projects that sort of have a similar flavor to them. Sinner is about data generation, but the user gives us small examples of what they want in the generated data set, and then we construct from it the data generation script. And that script can support things like statistical generation, or sort of custom generation, or even domain generation. And I actually have a working version on a tablet here, so if people want to play around with it, I'm happy to sort of fire it up and have you sort of generate data. Then there's Seer, which is about text extraction. And the idea here is that you have these documents, you highlight what you want to extract, and it will construct the data extraction script. And this is sort of joint work with IBM, where they have their own platform for text analysis and text extraction, and we've created this interface for them that allows us to create these extraction rules from a few examples. And then YFlow is about debugging data pipelines by examples. This is more of a negative results work. So it was actually a big project that we did. It took about 1.5 years of us fiddling around with different ideas, none of them quite working. But that's because debugging is a very hard problem in general. And I'm happy to talk about some of what we did over there. And then Package Builder, this is more of our database work. And it's really about extending the relational paradigm so that instead of returning queries that return tuples at a time, we return sets of tuples at a time. So if you have any questions, I'm really happy to answer them. I also have a tablet with Catch loaded on it, so you could sketch to your heart's content and sort of get queries and see how it works. You could try the regular expressions or the relative positioning to get ordered time series queries as well on it. And as I said, I also have Sinner available to play with.
We have time for some more questions.
So I do have a question. So you made a big hypothesis that the user's intent is to retrieve fragments of time series or time series that match a particular sketch. And you used the users in the first slide that you showed us, which is a particular population. And I have two questions. First of all, does your hypothesis actually apply to that population? You didn't tell us the results of how well the evaluators matched the sketches to the original data series. I'm curious about those results. But the bigger question is what happens if you move to a different class of users, and the time series that come to mind are in financial data, and they are financial analysts is very interested in the scale of the increase or the decrease. If it's 5%, if it drops more than 5%, then we are bankrupt. Right. If it's only 3%, it's a big difference. So I was wondering if you looked at different kind of types of users.
Okay. So the first question, did we validate again with the crowd workers that we've used to generate the sketches? And in the sense that you're asking, no. But in the sense that we've used their sketches and the reference regions, and we did that targeted search evaluation, we did. It's a bit tricky to give crowd workers exploratory search tasks. Crowd workers in general are very tricky to work with and sort of getting them to come up with queries, because their incentives sometimes are misaligned with what you want to do. So it's much easier to bring in 16 users in a controlled user study and get them motivated or interested in the data set and ask them to run exploratory search and then rank the results for you than it is to ask a crowd worker to sort of get any motivation behind the data set and explore it, right? So that's why the two studies were done on different populations. Now, Catch was motivated by talking to different people. Some of them are economists, for example, who have this problem where they're trying to look, for example, for depression patterns. And when you talk to an economist and you ask them to define what a depression pattern is, they don't have that exact definition that a finance person might have, which is like, you know, over a span of 2 years, this price needs to drop by this much, or inflation needs to grow by that much, right? To them, it's more, the price, the inflation should grow. By how much? They don't have that much. How long a depression lasts, that's a question that befuddles most economists, right? So Catch is designed for those kinds of queries. Now, if you have a very precise idea of what you want, then I'd say maybe Catch is not the right tool, right? There are better tools to do this. And the literature in time series querying is quite vast. So there are tools that would allow you to say, I'm looking for an increase in 5% or less or more. And there are tools that would support that, and I'd say they'd be better because their language is a lot more precise. Now, one of the things you could do with Catch is annotate, right? And your annotations can allow you to be that precise. The other feature that I haven't shown is that we sometimes look at a sketch and then transform it to a predefined query, right? So if you draw something like that, we could say, well, is this an exponentially increasing line where this is the equation of the line, right? So that would allow you to sort of perform very precise queries of that nature by taking your sketch and transforming it to a mathematical representation. That said, I don't think that's the primary audience for what Catch is. It's really meant for people who have patterns that are not necessarily precisely defined, but they have sort of a general trend that they're looking for. So economists really liked working with Catch in that sense. Yes?
I have a question. When you compare two different time series, right, that seems to be a very compelling scenario. But in that scenario, if I draw a pattern for the two time series, the relative sizes might matter. Like I might say, if there's a little bit of drop in unemployment, but that is followed by a large drop maybe in house prices. So do you take that into consideration, or would you match any kind of scale pattern on one time series with any scale pattern on the other time series?
It's the second thing. We don't really. It's a good point. We should. I think we should actually look at the whole canvas and consider the scales of the two, and then sort of uniformly scale both in unison, but we don't do that actually. So each one of those is independent. Yes?
So there was actually work at Viz last year that addressed essentially the question that you brought up about matching two. You have two time series, or you have the results, right, and you're matching the how different are these time series perceived as being.
Mm-hmm.
It's a sort of pairwise comparison, so kind of the backwards problem. And they found that some of the same things that you found in terms of people seem to be sort of scale free with some of their judgments about similarity. But they found that the way that you visualize the time series seems to impact those judgments. So for instance, if you visualize it as like a color field instead of a line graph, then just people's perception of what counts as an important difference between the two just goes out the window.
Yeah.
So I'm wondering if there maybe are there building blocks that are sort of similar to your scale-free segments that you could imagine constructing maybe for different representations or even for different problem domains, right?
That's a great idea. I mean, we haven't thought about what if I represent the time series through a different visualization? Is there something else that what stands in place of the sketch at that point that allows you to sort of work, for example, with a color scale rather than There's also this work by Jeff here on like the time horizons where you sort of overlay the time series so that they all fit within a certain, that kind of visualization, and how do you sketch for that? I don't know, right? It's an interesting question that we actually thought about, and then sort of said, well, we can't really make much headway in that problem. The thing, though, that you did mention that's really what we saw is that how you visualize something really matters for people to judge similarity. And so that is something that, you know, our tool, when we sort of visualize results, we try as much as possible for the two to sort of match. So we can, in a way, zoom into a match when they select into it so that the two look similar in a way. And that's important because you remember when I gave that example of drawing a straight line, well, you could match it to something that's vertical or something that's horizontal. And really, how you visualize it depends, sort of gives the user that sense of similarity. Yeah, but I think that's an important thing in that, you know, sometimes when we think about matching things, we don't really think about how the users perceive them at the end, and we have to think about them. We have to think about that. There's also, like you said, lots of work in terms of clustering time series based on how similar they are. And it's very interesting because you throw different algorithms at it and you get different clusterings. And, you know, what does that mean? So that's an interesting problem as well. Yeah.
So how about adding another dimension? I mean, I'm looking here at this classic investor's shape called a cup and handle, right? And that has two dimensions to it, one of which is this shape that looks like that. And the other is that the right-hand piece here has lower trading volume. So the signal that you're looking at is price. So one could maybe think about people sketching that by pressure or width of line or something like that.
Okay, so that I think I get your point. Suppose I have sort of a volume graph where I don't necessarily want to sketch a pattern, but I have, let's say, a bar chart would be a more accurate representation of what I'm looking for. Is that so? Well, I know what the cup and handle pattern is, but are you referring to the handle sort of being within a certain bound?
Well, it's more that I think that it's a lower trading volume. So there's two variables here. There's price range per day, and then the volume as well.
So is it a 3D? Like you could plot it as a 3D graph?
Yeah, probably. Yeah.
So one possibility, these are two different variables, then there are two different time series, and so I could use our relative positioning to sort of draw the cup and handle for one, which is the price, and then what I require for the volume on another, and make sure that they overlap, and that will give me exactly what you want.
Okay. Right.
The other thing that I want to point out is that we really wanted to look at that specific problem of using a sketch to match things with time series. Now, that does not mean that we think of sketch necessarily as a complete tool. We think of it as an idea, and you could use that interface and plug it into, say, a better time series querying tool that has lots of other features. Right? So time series, when dealing with time series data, there's a lot more than just, you know, you might be interested in looking for repeated patterns or motifs in your time series data set. Right? And so Sketch does not, you know, does not stand in place of these features, right? It's just a feature that you could add. And we've sort of really studied what it means to support that feature. Yes?
So you said that 9% of the people were the fine squigglers.
Yeah.
Have you thought about classifying the type of person who's making the query and using that as a signal for your results?
No, but they're crowd workers. And the reason why we didn't want to go too far down that lane is that there is this idea of the user learning, right? And if they learn that they could just give the pattern in its most abstract sense, then they won't be the fine squigglers, right? Because the fine squigglers are not necessarily, are not capturing anything other than, I expect there to be some noise, right? And if they use our tool and they realize that it tolerates noise, then they won't do that in the next iteration of using the tool. So that, we haven't really tested it, but when we did the user studies, that's what we observed, right? That there's this quick learning after trying out the tool. And even if they started with the quick squiggles and stuff, by, during the time that they were playing with the tool, they figured out that they don't need to do that. But because we're using crowd workers, we can't necessarily go back to them and tell them, don't do this, right? And we didn't want to do it, right? Initially, we just wanted to get what people would sketch.
Okay. All right, thank you so much.
Thank you.